All right, so today is our second topic of the function course. We're going to have a look at a very simple form function, which is called linear function. And this is the course outline for today. Specifically, we're going to have a look at definition and its graph. And then because the graph of a linear function is a line, so we'll review uh, the concepts of lines in 2D space. Then last, we'll have a look at how we can do linear optimization. Okay. First, let's have a look at the definition. A function with this form, y equals ax plus b, is called a linear function. So any function can be written in this form is called a linear function. But a and b are constants. So the graph of such a function is a non-vertical line. Why is that? Because, yeah, you can explain this.
um, it would be like the denominator would be zero if it was a vertical line.
Yes, so yeah, so you explained that the reason why it's a non-vertical line. So can you explain why the graph of this function is a line?
Because the degree is one.
Yeah, so the question is why the graph is a line if the degree is 1? So we can actually consider this question like this. So first we can consider this question, consider this function as y equals a times x, right? So let's just leave b aside. Then we will have y over x equals a constant number, right? If y equals x is a constant number, if you consider this uh, in a 2D Cartesian plane, that means the y coordinate over the x coordinate of any point equals a constant number. That means these points should be in a straight line, which crosses the origin point, right? Because y over x is simply tangent theta here. Theta has initial arm here and terminal arm here. If tangent theta is a constant a, then they should be all coterminal here or here. So these points should be on the same line. And then if you simply add a b, we simply translate the whole graph up or down by b units. So it's still a line, right? So as you can see here, the graph of a linear function is a line. So let's briefly review concepts related to lines in the 2D space. Okay, first of all, make sure you know how to calculate the distance between 2 points in the 2D Cartesian plane. Are you familiar with this already?
Yeah.
Okay, so just pass this, and let's do a quick quiz. So if I tell you there are 2 points here, M and N, whose coordinates are 2, 3, and negative 4, 1, what is the distance between these 2 points? Okay, let me know if you finish, okay?
2 square root 10.
Yes, that's simply square root of the difference between the x coordinates, which is actually 2 plus 4 squared, then plus the difference between the y coordinates squared. And we'll get 2 square root 10. That's the distance between 2 points. Okay, very good. And how about this one? Again, that's square root of the square difference between the x coordinates. plus difference between the y coordinate squared, right? Which is square root 10. Okay, very good. And next, make sure you know how to calculate the coordinates of the midpoint of 2 points. Again, are you familiar with this formula?
Yes.
All right, so basically the x-coordinate should be 1/2 of the sum of the two coordinates of two endpoints, and then same for the y-coordinate of the midpoint. So again, let's see a very quick example here. If you know the coordinate of P and Q, then midpoint of segment PQ can be easily calculated using this formula. So suppose this is Q, this is our P, and then let's say the midpoint is M, whose coordinates are xm, ym. Then we can easily see xm equals 1 over 2 times the difference between the x coordinates of the two endpoints. Sorry, the sum of the two endpoints, which is 2 plus -7 equals -5 over 2, right? Similarly, for ym, that's simply 1 over 2 times 4 plus -2. So 4 minus 2, which is 1. And therefore, we know the coordinates of the midpoint M is -5 over 2, 1, right? Okay, so I'll just pass the next example because basically they're the same. Yes, you can. Yes. The x-coordinate of the x-intercept is simply -1, right? Because from the equation of this line, we know the slope of this line is 1 over 2. So the desired line, this line, has a slope -2, right?
Yeah.
And our desired line passes through this point, whose slope is -2. So this line has this equation, y minus 4 equals -2 times x plus 3. And we only want its x-intercept, so we simply let y equals 0 to find x. So -4 equals -2x minus 6, then -2x equals 2. Therefore, x equals -1. So that's our x-intercept. And rigorously speaking, x-intercept is a point, so it's better to use -1, 0 as a coordinates of a point. But it's also okay if you simply state x equals -1, because by default, the y coordinate of x-intercept is always 0. So both ways are correct. Okay, any questions so far? No? Okay, then next, let's revisiting the concept of the inverse of a function. Remember when we talked about the property of the inverse of a function, one of the properties states that the graph of a function fx and its inverse f inverse x are symmetric with respect to the line y equals x, right? Can you recall that?
Yeah.
So now as as we have just learned the property of lines, can you prove this property rigorously? Can you show why the graph of fx and inverse f of x are symmetric with respect to the line y equals x?
Um, because the degree is one, there's no exponent.
Whose
And
degree is 1? No, no, I mean, well, actually, fx can be any function, right?
yeah.
For example, if you have a quadratic function like this, well, no matter whether its inverse is a function or not, the inverse of this function, the graph of the inverse of this function, is always symmetrical with the original function in the line y equals x, like this. Can you prove this?
Well,
Or sometimes you may have a function, for example, like this exponential function, and its inverse is logarithmic function. Those graphs like this, they are also symmetric with respect to the line y equals x, no matter what the function is. The function is always symmetric with respect to the line y equals x to its inverse.
I'm not sure how to prove this.
Okay, so let's separate this question a little bit. This really checks your understanding of the property of lines or their relationships. So basically, if you want to prove this, then we need to prove that any point on fx, so suppose this is a curve of fx, no matter what it is, any point on fx must be, if reflected in the line y equals x, must be on the graph of f inverse of fx, right? And vice versa. You also need to prove that any point on the inverse of fx, if reflected in the line y equals x, is also on the graph of fx, This way, you can prove they are actually symmetrical with respect to the line y equals x, right? Does that make any sense?
Yeah.
And the method should be the same. So as long as you can prove the first half, then the problem should be solved. Okay, so let's see how we can do this. So let's say proof. We need to prove that any point on the graph of fx, so I'll just say fx here to save some time. If reflected in the line y equals x is also on the graph of f inverse of fx, and vice versa. So we'll just prove the first half and use the same method to illustrate. You can do the same thing vice versa. And let's draw some variable a's here. Let's say, okay, this is the line y equals y equals x. And suppose we have a point A here. Coordinates are x1, y1. Then we want the reflected point in the line y equals x, whose coordinates are x2, y2. That's point B. Well, there's also a point of intersection. Let's call it point I, whose coordinates are x0 and y0. So let's say suppose A, x1, y1 is any point. Okay, note, it's any point, not just a specific point. It's any point on y equals fx, on the graph of y equals fx. Then, because this point is on that graph, it will satisfy this equation. So then we have fx0 equals y0, right? Then we let b x2, y2 be the point. If x1, y1 is reflected in the line y equals x, then we know the slope of the line AB is actually -1, right? Because this line has slope 1, then a line perpendicular to this line must have a slope of -1, right? Again, we can let I be let I x0, y0 be the intersection point between y equals x and line AB. Then what will happen? What do we have here? Then we have first, write it here, x2 equals 2x. Okay, so if I is a point of intersection and I must also be on y equals x, right? So we can let the y coordinate of I be x0 as well, right? So let I be the intersection between y equals x and AB. Then we have x2 equals 2, x0 minus x1. Can you see why? Because we use the midpoint formula here, right? Similarly, y2 equals 2y0 minus y1. And we also have y1 minus yx0 over x1 minus x0. That's the slope of AB, right? Which is -1. And this gives us y1 minus x0 equals x0 minus x1. And this gives us 2x0 equals x1 plus y1, right? Okay, so let's call this number 1 and this number 2. Then we can insert number 2 into equation number 1. So, I mean, equation number 1 is actually a system of linear equations. If we insert 2 into 1, then this will give us, first of all, x2 equals, substitute 2x0 with x1 plus y1 here. So minus x1, which is y1, right? And similarly, y2 equals x1. Can you see that? X2 is actually y1, and y2 is actually x1. So, what do we have here? Inverse of f of x2 equals, so what is x2 here? We have just proved x2 is actually y1, right? So that equals inverse f of y1. What is inverse f of y1? We know that under the effect of f, it maps x1 to y1, right? So that means if we reverse the relation, then under the effect of f inverse, it will map y1 back to x1. So that's why we have inverse f of y1 equals x1. You see that? And we have also proved x1 equals y2. So we have proved f inverse f of x2 equals y2. So what does this mean? This means if you insert x2, y2 into the equation inverse of f, it will satisfy that equation. So B is on the inverse f of x, right? So we have just proved if you select any arbitrary point on the graph of fx reflected in the line y equals x, then that reflected point B must also be on the graph of f inverse of x. You can also use the same method to prove that if you select any arbitrary point on inverse f of x reflected in the line y equals x, that reflected point is also on the graph of fx. Therefore, we can actually prove the graphs of a function fx and its inverse are symmetric with respect to the line y equals x, right? So again, I'm not gonna write all the proof here. Try to complete this by yourself. Okay, really check the understanding of the lines, understanding of the lines, equations, slopes, perpendicular, these concepts. Okay, any questions?
No.
All right, so next, let's have a look at the concept of linear inequality. So you already know how to graph a linear equation. So their graphs corresponds to lines, right? For example, you know how to graph x minus 3y equals 9. This is a line. So how about if I change equality symbol to inequality symbol here?
Could you go back one time and finish taking that?
Okay, here. Okay, don't worry. I'll put it on my YouTube channel. You can reference it here. There. Okay.
Yeah. Good.
Okay. So next, let's have a look at how you can graph a linear inequality. So you already know how to graph something like this. Y minus 3y equals 9. That's actually a line, right?
Yeah.
So how about if I change the equality symbol to greater than or equal to? What does this graph look like?
It's. Do you want me to try it or?
Yes, please. Have you studied this before?
Yeah.
That's actually a region, right?
Yeah. Just like this.
Okay, you can compare yours with my solution. So usually when you consider a inequality that corresponds to a region, you have to consider boundary force, which corresponds to the equation of a line, right? So first, let's let's see, consider the corresponding, you could say consider corresponding line first, which is x minus 3y equals, oh, sorry. First of all, let's convert this to a functions form. So this is equivalent to, say, 3y is less than or equal to x minus 9, which is equivalent to y is less than or equal to 1/3 of x minus 3, right? Let me say consider corresponding line. And the corresponding line is just change the inequality symbol to equality symbol here. Y equals 1/3 of x minus 3. So first of all, we can draw a graph of that line, right?
Yeah.
So what does this line look like? It has a positive slope and it crosses the point 0, -3, which is something here. And when x equals 9, y equals 0. So x-intercept is here. So basically, this is our line. This is our line. Again, not necessarily to scale, as long as you keep all the elements in their right relative positions. So this is the line y equals 1/3 x minus 3, right?
Yeah.
But we have a equal symbol here, less than or equal to. This means if you insert any x there, y is either on that line or below that line.
Oh yeah.
Smaller than means below, right? So you need to shade it like this. And particularly also shade the boundary here to indicate the boundary is also included because it says less than or equal to, right? Right
Yeah.
here. Okay, and let's see another example. Yeah, basically you need to study the line first, corresponding line first. Okay, sometimes we also need the graph of a system of linear equations. Something like this, graph the region of points that satisfy both inequalities. In that case, we need to find, this is a region, this is another region, right? So if you satisfy both of the inequalities, that means you need to find the overlapped area of the two inequalities, right?
Yeah.
Okay, you can try to work this on your journal and let me know if you finish. Then you can compare your result with mine. Okay. All right, thank you. And let's have a look at this question together. Again, we need to consider corresponding lines. So first of all, I like convert. I like to convert both of the inequalities by separating the x and y. So first of all, we know 2x minus y minus 4 is less than 0 is equivalent to y is greater than 2x minus 4, right? And then corresponding lines can be represented in this way. Line, we call line L1, which is y equals 2x minus 4. This is the boundary of the first inequality, right? And okay, I'll write it here. So in my graph, first I'll graph the first line, 2x minus 4. Well, x equals 2, y equals 0. So this is negative 4, this is 2. That's our first line, right? And for the second one, 2x plus 3y minus 6 is less than 0. That's equivalent to y is less than negative 2 over 3x plus 2. And then let's call it line L2, which has a negative slope. So it should have a direction like this, right? Not the one on your graph. So line 2 has the equation y equals negative 2 over 3x plus 2. And that's the line will cross the point here. Okay, this one here is 3. This one here is 2. Again, not necessarily to scale as long as you keep all all the elements in their correct relative positions. That's fine. All right, so the first inequality is above that line, right? So it should be here. Okay, this is line 2. We have a region that is above line 1, right? Here. This is all the region above line 1, right? But we also need all the region that is below line 2. So what is the overlapped area? Can you find that? We need the region below line 2. So the overlapped area is actually here. I'll use another color here. This is the overlapped area, which corresponds to the system of two linear inequalities. Erase this, erase this. So this is the desired area. You see that? So anything else we need to pay attention to?
Um, should the lines be dashed? Because
Yes,
it's great.
yes, very good. You observe that because we have strictly less than or strictly greater than, right? So
Yeah.
we have dashed lines as the boundaries, which means the lines or boundaries not included. Okay, any questions? All right, then let's see. Last topic in this lesson, we're going to briefly introduce linear optimization. I'll use an example to illustrate the concept here. So, can you find the maximum value of an expression 2x minus 3y such that the following three inequalities are satisfied? Okay, I'll give you some time to consider this. Any thoughts there? Let's have a look at the solution together. So basically, this corresponds to a region, right?
Yeah.
You need to find the region first. And in order to find the region, usually we'll consider the boundary lines first. So let's call them region number 1, 2, 3. Region number 1 is equivalent to 3y is less than or equal to 2x plus 6, which gives us y is less than or equal to 2/3 of x, then plus 2. Let's call this boundary as line 1. Then the corresponding line is y equals 2/3 of x plus 2. And we'll draw this line on our 2D Cartesian plane. And then let's consider the second inequality, which gives us y is greater than or equal to negative 2x plus 4. Then we consider the corresponding boundary line L2, which is y equals 2x plus 4. Another equation of line. And equation number 3, inequality number 3 is x is less than or equal to 3. This is very easy. This is all the region to the left of x, right? So the boundary line, let's call it L3, is simply x equals 3. So the region corresponds to the overlapped area of the 3 regions. So let's draw it onto the Cartesian plane. Then this is our x and this is our y. So the first line is here, somewhere here. This is our line L1. This point here is 2. This point here is negative 3, right?
Yeah.
And for L2, negative slope, so something like this. This is point 4 and 2 here. This is our L2. L3 is simply a vertical line, like this. This one here is 3. Again, not necessarily to scale, but you need to keep all elements in their correct relative positions. Okay, so what is the overlapped area? Your region must satisfy all of these 3 inequalities, right? So that region must be here. You see that? Below L1, above L2, to the left of L3. So this is our L3. So what this question really asks is, in this region, you have infinite number of pairs of infinite number of pairs of x and y's, right? Which pair of x and y can make 2x minus 3y be the largest? Also, the boundary is also included. In this triangle region, which pair of x and y can make 2x minus 3y be the largest? So how can you approach that question? Okay, we're here now. So from here, okay, just follow me. We can let 2x minus 3y equals a number such as, well, let's say k. And this is actually a line, right? You see that?
Yeah.
So this gives us 3y equals 2x minus k. They are equivalent, and equivalent to y equals 2/3 of x minus k over 3, right? So this is actually a line with slope as 2 over 3, something like this. So basically, you have a slope slightly lower than 1. It's a line like this, right? I put it here. What we don't know is the y-intercept, right? The y-intercept is negative k over 3. It could be anything, correct? So this is actually a family of lines whose slopes are all 2 over 3 with different y-intercept, right?
Yeah.
So this line can move vertically up and down, but with the same slope, right?
Yeah.
So the question really asks that where should x and y be in within the shaded region such that we have a maximum of k value, right?
Yeah.
So the only pair of x and y that can make the k maximum must be achieved at one of its vertex, one of its vertices, right?
Yeah.
Can you follow me?
Yeah.
Because it's a bounded region bounded by 3 linear equations. And we want the line here to have a maximum y-intercept. Sorry, actually smallest y-intercept such that k is the largest, right? If k is the largest, then the y-intercept must be the smallest. And then
Yeah.
it can only be achieved on one of its 3 vertices. Of course, if you have a bounded region like this, again, this concept also holds true. It can only be achieved on one of its vertices, right? So we can just calculate the coordinates of each of the vertices, P1, P2, P3, and see which pair of coordinates can make 2x minus 3y be the largest, right? You follow me?
Yeah.
Okay, so in order to do this, let's first find P1. So how do we find P1? We have already talked about this. You simply combine the two equations, two corresponding equations. P1 is a point of intersection between L1 and L3, right? Simply combine these two equations, which is equivalent to, what is L1? L1 is y equals 2 over 3x plus 2, and L3 is simply x equals 3. And this gives us a unique solution, x equals 3 and y equals 4. Therefore, the coordinates of P1 is 3, 4. And similarly, using the same method, we can find the coordinates for P2, which is the point of intersection between L1 and L2, right? And then correct their equations there. Y equals 2/3 of x plus 2. The equation for L2 is y equals negative 2x plus 4, right? You solve this question. Okay, solve this system of equations. What is x and y here? Yeah, tell me what are the coordinates for P2. And at the same time, I'm working on P3. Yes, that's the same with my calculation here. And then you can also calculate the coordinates for P3, right? P3 is point of intersection between L2 and L3, and that's relatively easy. P3 has coordinates 3 and 2. So we know the coordinates for P1, P2, and P3 now. And we know that one of these points can make our desired expression here be the largest one. So we'll just compare which point can make them the largest. So usually we'll make a table like this. We check each of the vertices, and the target of the optimization is to make 2x minus 3 be the largest, right? Okay, so the first vertex is P1, 3, 4. Second one is P2, 3 over 4, 5 over 2. 3, 3, negative 2. Then we calculate each of the two x minus 3y. For the first point, 2 by 3 minus 3 by 4, which equals negative 6. For the second point, 2 by 3 over 4 minus 3 by 5 over 2, which equals negative 6, right? For the third point, 2 by 3 minus 3 by negative 2, which is 6 plus 6, which gives us 12. And we see this value is the maximum one out of the 3, right? So we can make the final conclusions. Therefore, we know when x equals 3, y equals negative 2, which is within this region, the maximum value of 2x minus 3y is 12. Okay, let me know if you're finished. All right. All right. So what is the main takeaway here? Let's try to summarize the method we use here. So suppose we must minimize or maximize or optimize a linear expression here. This is our target. This is called a target. Suppose the target is a linear expression in one or two variables, such that the variables satisfy a set of linear inequalities, such like this. This is called a set of linear inequalities. This is our constraints. Basically, you consider the optimization in these constraints. Usually that corresponds to a bounded area. And suppose further that the set of all points that satisfy the inequalities in a bounded region. This is very important. Sometimes if you have an open region, sometimes you may or may not have the optimized value for your target function. So instead of extending indefinitely in some direction, if you have a bounded region, then the inequalities if you have a boundary region and the inequalities are non-strict, so that boundary points can satisfy them. Okay, sometimes if the boundary cannot be reached, you cannot find the optimum value. So this is also important. The inequalities are non-strict, so that boundary points satisfy them. Then the point inside the boundary region that optimizes the desired expression must be a corner or a vertex of the region, something like P1, P2, and P3. The reason why this is true, because we have already analyzed the reason, right? Basically, you're trying to move a line up and down and try to find either the maximum or the minimum y-intercept. So it must be touched at some point on the vertex, right? And of course, sometimes if you have an open region, sometimes it's also possible to optimize your target expression, and sometimes not. Yeah. So this is a method that we can use to optimize a linear target function. All right. Do you have any other questions?
No.
Okay. So let's make a summary of this lesson. So in today's lesson, we have talked about the definition and graph of linear functions, right? Linear function has this form, which is basically the simplest form of functions we have learned so far. Y equals mx plus b. And the graph of linear function is actually a line, sometimes with a positive slope, sometimes with negative slope, or sometimes even zero slope, right? But if you can write the line in this form, that does not mean this means this line cannot be vertical, cannot be a vertical line, right? And then we talk about the lines in 2D space. Lines are a set of points that satisfy some sort of equations, and this equation is usually linear equations. And make sure you know how to calculate distance between 2 points, midpoint coordinates of 2 points. Then section formula asks us to section formula helps us to find a point divides a section either internally or externally, and with a ratio lambda. Lambda is the ratio between AP over PB. Do not confuse the order. Order must be in this one, APBP. Sorry, APPB. Make sure you know the two formulas. They are different. And midpoint is actually a special case. Midpoint formula is actually a special case of the section formula, right? And also make sure you know the definition for slope and intercept of a line. And also be able to express the line using 4 different types of equations, such as point slope form, slope intercept form, general form or generic form, and two intercepts form. Okay? And in order to find the intersection between two lines, simply combine the equation of two lines. If you can find a unique solution, this means two lines intersect at a unique point. Otherwise, if you have infinite number of solutions, this means these two lines are all on top of each other. Otherwise, if you can't find any solution, this means these two lines are parallel, right?
Yeah.
There are 3 different positions. And parallel lines and perpendicular lines, make sure you know how to determine whether two lines are parallel or perpendicular. And also make sure you're able to find the region that corresponds to a linear inequality or system of linear inequalities. And in the end, we also talk about how to do linear optimization. If you have a linear target function such as 2x minus 6y, this is a target function. You want to either maximize it or minimize it within some bounded region. Usually, the optimized value can only be achieved at the one of the vertices. So usually first we find that region first, and then calculate the coordinates of these vertices and compare which vertex can make the target function be the optimized one, right? Okay, that's pretty much about it, and I'll see you next time.